Mars is screaming with secrets. Are you listening? Join renowned astronomer and History Channel analyst Mark D'Antonio for a journey across the light years.
We're looking at stars that died before we were born and planets that might just be looking back.
From the mysteries of deep space, live feeds from the Sky Tour live stream telescopes, we're bringing the heavens to you. It's the Sky Tour Radio with Mark D'Antonio. Look up, look up, look up, look up. The show is about to begin.
Hey, welcome everybody. Welcome to Sky Tour Radio. It is I, Mark D'Antonio, and that guy over there is our esteemed producer, Bill Skywatcher, who is sitting in with us tonight. Tara is taking the day off. She's not feeling well, but I've got a full show ready to go. So, she said go for it, and Bill said I'll go for it, and so we're doing it. I'm not sure what's going to happen. It could be dangerous,
Can I raise my hand to open up with something first?
Go right ahead. You can go right ahead. Bill's going to ask a question. See, that's what he does. He always interrupts me, but it's all right. It's okay. It's Bill.
Well, first, I want to say hello to everyone that's watching and listening right now on the Unexplained Network and also on Sky Tour live stream on the Tube of You. I have to say it that way because we are also live on my TikTok, which is pretty cool for those that are tuning in on my TikTok channel.
Yeah.
But Mark, before you get into your main topic of discussion tonight,
sure.
I have 2 questions.
Okay.
You were right. First, Avi Loeb is talking about that, and I know this is rehashing an old subject, but it recently just passed its closest approach to Jupiter, which is 3I Atlas, having some type of a nuclear fuel properties.
Yeah. You want to know about that?
Yes, please.
Okay. Well, first of all, the nuclear properties he's talking about are a certain isotope of hydrogen called deuterium. Okay. And hydrogen has a proton and it has an electron whizzing around, right? That's the idea of a hydrogen molecule or hydrogen atom. But if you add a neutron into that hydrogen nucleus, which can happen, you have something called deuterium. And so when we have deuterium out there, what it shows us is that the comet 3I Atlas, the object 3I Atlas, has this deuterium abundance. And we have a deuterium to hydrogen ratio that we look at. And the deuterium to hydrogen ratio of 3I Atlas was a lot bigger than it should be, or that we're used to seeing. But then again, we're not used to seeing objects like 3I Atlas, are we? This is an interstellar comet. It came from very, very far away. It could be literally maybe twice as old as our star system, our solar system here. So if it's around 7 or 8 billion years old, it probably came from one of the very first planetary systems to be created in our galaxy, potentially. So one of the first, I should say, star systems ever created. So here's the thing about the deuterium. Deuterium isn't created in the comet. It arrived with it. And that's because most of the deuterium that's out there was created when the Big Bang occurred. So where did it go? Well, it ended up getting frozen into other compounds out in the universe and in dark clouds and so forth. And if you happen to be a cometary object passing through a dark cloud for billions of years, you're probably going to acquire some of this elemental, or should I say, early cosmic abundance of deuterium that was created. And that's probably what's happened with this. So this deuterium content that we see in it is likely due to its origin being so old and going through these dark clouds. It acquired this Big Bang era deuterium that was sitting out there potentially. Now, obviously, there's another point of view that Avi Loeb talks about, and he thinks possibly we're looking at maybe a abundance of a material that might be stored. Deuterium. Why is that important? Because deuterium is also a fuel, a nuclear fuel. So depending on how the ships are propelled, if it's a ship, then maybe the deuterium is a propulsion element, a fuel. My personal feeling is I think it's naturally produced.
Huh.
And the reason I think that is because um, we know that deuterium was produced in the Big Bang. We know that deuterium hides in some dark clouds, and we know that this object is very old. And we do know that cold, dark spaces will allow a certain amount of deuterium to be deposited on it. I mean, the way it's deposited, if you want to look it up, to anyone who's interested, it's called chemical fractionation. Okay, now chemical fraction, like fractionation. All right, so that process is the reason why there's deuterium in 3A Atlas, in my view. I know Avi. I've talked to him, and we've actually done a few programs together, but separately, but together, for different stations, different podcasts together. But I will say this: um, I really admire the fact that he's willing to step out
Huh.
and make the claims that he does, because what he's saying is something that will eventually bear fruit. Because I'm certain that the universe is a populated universe. It's the title of my book, right? Yeah. So I believe that at some point or another, he's going to really be right on the mark. I think this one, maybe not so much. But to look at an object as a potential extraterrestrial vehicle slash UAP is a very good idea, because we have to start getting used to the fact that we're going to see one eventually, and we're probably going to catch one sooner or later. So might as well put anything we see through the ringer, right? To see if maybe this is what we're seeing. I'm all for it. And I don't, if he's wrong, he's wrong. But guess what? He's right in that he has to and should ask those questions. It's very important to ask those questions and do those analyses.
I agree.
Yeah, see?
Second, and it's not a trick question, even though it may happen on my birthday, April Fool's Day, Artemis 2, the mission.
Yeah, I saw that. The potential mission. I have my Artemis shirt. I have all my Artemis gear. But you know what? I'm hopeful that they'll launch, because it's going to be basically a return to the moon for the human race, isn't it?
But obviously there are certain risks, health risks especially, and I'm not just talking about the physical risks of the craft itself, but what about the radiation? Have they done anything to prevent them from being affected from the radiation on their trip?
In the same way that the astronauts going to the moon and the Apollos were protected.
Exactly.
But they did see, I actually did for the show What on Earth, because a lot of the different networks have used me as a science guy to explain some of the phenomena they've seen. And they wanted me to talk about how the astronauts on the way to the moon would wear a dark hood. It was an experiment that they wanted to do, or they were asked to do. And they would count the number of flashes they would see in their vision. What are those flashes? Well, you don't really see them here on Earth, do you? That's because it's just not that common here on Earth, but out in space it is. You're seeing cosmic rays striking you and striking your optic nerves.
Wow.
And hitting your retina. So you're actually watching the cosmic ray strikes. These little micro bullets are hitting you, and they could hit you by the hundreds or more, depending on how you're oriented, where you are, and whether you've got a planet blocking you from some of them, that kind of thing. So that was one of the experiments, and they asked me to explain what those were. And the cosmic rays, as far as we know, we're getting bombarded by them all the time. So as far as we know, they're not killing us, but they are, they are prevalent, in the same way that we have millions of neutrinos running through us from stars all around us in the universe, and they go right through the Earth and pass right through you. They're passing through everybody watching right now by the hundreds of millions. and they're coming from all over the universe. If you could see what was actually racing toward us in the universe, you'd probably curl up in a corner and go, no, 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 go away. Because it's like, it's just constant from all directions. You got cosmic rays, you got neutrinos, okay? And you got all kinds of other radiation coming from the sun. You've got ultraviolet radiation that makes it down to the surface. You've got all kinds of, you've got actually radiation in your own home that's being radiated, okay? That's coming out and going through you. And so if you could see all this, and that's not even talking about cell phones and 5G and Wi-Fi everywhere you drive, it's not talking about any of that.
Right.
So we are surrounded by an electronic cloud, a nightmarish cloud of competing signals that all want our attention, some of which don't even know we're even there, like the neutrinos, and to trap a neutrino, which is a high energy particle that has almost no mass and can zip out of a star when it's being made and almost leave completely unimpeded, right? Unlike a photon of light, okay? Now, the photon actually can get absorbed and re-emitted. So a photon's journey out of a star might go, it'll take it, if it's emitted at time 0 in a nucleus or a core of a star, it might be, several years before it gets out of the star. That same photon just bouncing around trying to get out, and that's bundles of energy. They're not even particles, okay? So, but neutrinos, on the other hand, they don't collide with anything. They basically go unimpeded, and only by chance can we trap a few of them and estimate how many there are out there in the universe. And we do this in deep mines that are full of this special water that will capture these neutrinos. It's pretty cool.
Wow.
Yeah.
Well, Daisy says this is going to conjure up some interesting dreams tonight.
And yes, it will.
And hello on my end to someone in Ukraine and everybody else, like I mentioned earlier, that is viewing and listening right now. Also, Mark, can you tell us a little bit? You've been busy this past week or so. Can you discuss anything about your appearance on an upcoming broadcast?
Yeah, I think I can say a few things. I was in Las Vegas to appear on a podcast called The Basement. It's a Y-Files podcast. If you're familiar with the Y-Files, WHY, AJ Gentile and Gino brothers. They had me come out and I did 90 minutes with them. And it was really fun. It was a really good time. They're very hospitable people. And they treat you very well. It was a very, very nice, very, very nice thing, so I was excited about that. And we talked about UFOs. We talked about some of my UFO experiences. We talked about Sky Tour live stream. Okay. See skytourlive.org up there in the corner. That's our remote observatories out in the Arizona desert. We go live, and there it is, my name right there, right? We go live on clear nights in Arizona, and we stream the universe live in real time. I mean, it's just a ball. And we talked about that. And so we had a very lively discussion. And for those of you that know the Y-Files, you know that there's a hecklefish. It's a goldfish in a bowl, and he kind of heckles you. Well, I interacted with hecklefish for about 45 minutes as well. So that's pretty cool. And for the Patreon subscribers, I think they get to see that interview. Really neat.
When is that supposed to air, Mark? Do you know?
I think it's not this week, but next week, if I understand them correctly. And that's okay. It almost didn't happen because there was some delays and stuff, but they ended up having to keep me an extra day and change my flights and all that. They did it all, so that was fantastic. But I ended up filming on Tuesday, not Wednesday, not Monday, as I was supposed to. But it was good, this all went very well.
For those that are viewing that may be new, can you just give them a little background on your telescopes and the location and a little specifics about the equipment? Because there could be some new viewers right now watching on my end, especially on TikTok.
Oh, yeah. Well, I'm an astronomer. This is what we look like. Okay. And I took my astronomy degree and decided to go into public outreach. Why? Because when I was young, I asked all kinds of questions to people that knew astronomy, and I needed to know the answers. And it was really one of those things about the night sky. How far away are those dots of light? What can be happening out there? Are there aliens out there, like I see on TV, in science fiction? Or is there anything out there that could foster life? How did life start here on Earth? I mean, all these questions. Typical questions that a 9-year-old has, right? No.
I would have loved to have seen your room, dude. I can only imagine what it looked like when you were a kid.
My room. Okay, when I started getting into astronomy, I bought star charts. My first star chart, some of the members of the audience will know what this is. Some will go, what? Was called a Scale-Nate Pleso. Yes, that's right. It was a chart of the stars, separate charts. And I bought that. It was a pride and joy. Then I bought the Deuterium Atlas. I bought Uranometria, okay, and several others. And these physical atlases were great. Then when I decided I really, really liked astronomy a lot, I locked myself in my room for 48 straight hours over a weekend. And I painted with glow-in-the-dark paint the entire summer sky on my ceiling.
Oh, I bet your parents were thrilled when they walked into that room 48 hours later.
Well, it may not have smelled too good, but I'll tell you this, they couldn't see a thing because I used glow-in-the-dark paint. The ceiling was still white, but when you turned off the lights, the roof was gone and you could see the stars. When I lay down, I look up, okay, there's the beautiful Cygnus, there's the Milky Way.
Wow.
Okay. Oh, yeah, and they were all in the right place. Every star was in the right place. Yeah, had to make sure that was true.
That's awesome, dude. That is awesome, Mark.
That's very cool. Yeah, and the thing is, I also took the time to, I guess this is where you say I don't have a life there. I also took every single star dot, which are little white dots on my Scale-Nate Pleso on my atlas, and I dabbed it with this glow-in-the-dark paint. Every single one. There were 16 charts. I have it in the back room. I should have brought it. And I made every single one of those charts a glow-in-the-dark chart by just dabbing every star. And there were hundreds of stars on each page, on each atlas page. Oh, man. Yeah, I didn't have a life. Boy, oh, boy. Anyway, it was kind of crazy, but it was actually a lot of fun. And the thing is, when you're doing something like that, you're learning. You're learning because, okay, you're making glow-in-the-dark stars. But it wasn't random. You're doing this. Well, now I'm doing Camelopardalis, the giraffe. Ooh. And now I'm doing Pisces, the fish. Okay. And now I'm going to do Orion, the hunter. Okay. And, 88 constellations later, all right, so when you get it all done, you've touched every single part of the sky. And because it's so intense and because you're doing it right there in front of that chart the whole time, you remember it. It's like you're immersing yourself in it. Like when you learn a language, the best way to learn is to go to the country, immerse yourself in it, and then learn in a class while you're immersed in it 24/7. That's literally the best way to learn a language, right? Well, it's the best way to learn a lot of things. So if you can immerse yourself in the science to some extent, then you have a great chance of actually making sure that you're going to retain a lot of it. And so I retained a lot of things because of that. Now, I did do this at age 10 or so. At age 9, I realized I was going to be a professional astronomer. And by age 10, I had my telescope and the Scale-Nate Pleso and the Deuterium Atlas and several other things. Okay. So I knew where I was going, And for a while, I went to inner space. Okay. Now, inner space is the ocean, deep ocean. And then chose outer space. So outer space, inner space here, not so much, right?
Yeah.
Right. But it's okay because I felt very strongly that the study of the universe was very important, and study of how things happen in the universe, why they happen, and how it affects us is really important. Is there anything out there that can hurt us? Is there anything out there that can destroy us? The answer is yes. And that's what tonight's show is sort of about. And we're going to talk about some of that.
Let's dig into it.
You want to?
Yes, let's do that.
Okay, we'll do that tomorrow. No, I'm just kidding. Yeah, so, if you do go to the Tube of You and look for Sky Tour live stream with Mark D'Antonio, you'll find the channel. We're on Rumble, Twitch, Trovo, Facebook, TikTok, Instagram. We're on all the social media, and you'll enjoy it. And you subscribe; it's all free. And we take the photos. That's the other thing I left out. We take photos using our telescopes, and then right then and there, I save them, and you see it saving. And within 30 seconds, you have access to that for free. And you can download that very photo and take it, no charge. Now, if you join the Patreon, which we have, well, then you can get highly processed versions where we remove digital noise, we remove the artifacts of the stacking process, it's called, and you end up getting a very clean-looking, frameable, beautiful print that you can put under a glass, you can put anywhere, and we also sell those. We have a online darkroom site where you can buy all the pictures that we have on canvas, under glass, as metal prints on metal, which is really cool. It's very vivid colors on those. And then after all that, you can go to our Etsy store and pick up, if you have a water bottle or something you want to put it on, we actually have those out there with our images on them that you can actually buy.
In Marianne's home, those were the examples of those, weren't they?
Yeah, but first of all, now you got to tell them who Marianne is. Come on.
Well, Marianne Robb is actually a dear friend. She's part of the UAPD.com.
Right.
She's also one of the essential persons involved with Sky Tour live stream and the telescopes in Arizona, along with Tara.
She's our chief financial officer.
Yes, she's an integral part of this whole thing.
35 plus year police officer in Arizona. Tara Daiulis used to work for the governor of Arizona. So she's the third person in our nonprofit organization. And, it was just like, there's a dream. The dream is to showcase astronomy for people and don't charge them a dime for it. Mm-hmm. See, I believe science is for everybody. I think everybody should be able to have science at their disposal. And, yes, we have to make a living. I know that. I don't take a dime from Sky Tour, not a dime. All the money that's donated goes back into Sky Tour. We pay $120 a month at Site 1. Okay, for Starlink, we pay $120 a month at Site 2 for Starlink, plus $400 a month to rent the building that second telescope is in down in Benson, on the Benson Plateau. Admittedly, we're on a plateau with like 9 other professional astronomers and myself. So we just basically want to meet the expenses, and we want to do some upgrades. We want to get some other telescope gear in there. And, so that's part of the process, Mm-hmm. It's all cool. So in our telescopes, we will show people many of the things that I'm going to talk to you about tonight. When I finally get to it, right? His fault. He's talking.
It is my fault.
He won't be quiet over there. I'm kidding. Right. So, and by the way, the reason that we started doing these observatory streams at all, him and Keith from P&K Space Imaging. Yeah. Oh, you should stream. What's that? I didn't even know. Now, I'm kind of like a streamaholic, right? Or something like that. I don't know. I mean, I stream a lot now. I actually have over 550 streams on our Tube of You.
He has to say it like that right now. He does.
I'm sorry. Yeah, our Tube of You channel. There's over 550 streams, and they are between 2 and 4 hours long. So I talk a lot. So that all said, one of the things that we talk about in the universe that is places that, as he said, could unalive you. But, I'm just going to have to go for it. Yeah, Deadly Places in the Universe is the title of the show. Okay, The Deadly Universe. I said deadly, right? Deadly. Yeah, that's deadly.
Oh,
That's
just
how-
keep saying it. I'm gonna go down. Oh my gosh.
actually, hopefully you won't. But anyway, just a lot of places, and these zones of avoidance in galaxies are places that have what are called neutron stars, white dwarfs, supernovae, and we're going to talk more later if we get to it about some of the most incredibly inhospitable planets the universe has to offer. And you won't believe what it's like on some of these planets. So anyway,
before you start, I'm interrupting him again. He's going to go nuts all night. We should wager a bet how many times I'm going to interrupt you. But what would be in our solar system? What would be the most extreme, inhospitable planet, moon, etc.?
oh well, in terms of inhospitability, obviously we have to talk about. Do we want to talk about gas giants? Where if you went into the atmosphere, you would just go all the way down until the pressure got so great you'd be crushed out of existence? Or you want to talk about out in the Kuiper Belt where the icy worlds are, where the temperature is almost absolute zero? So as soon as you stepped out of your craft, you'd freeze solid and that'd be the end of you. Do you want to talk about going to the sun where the surface temperature is 10,000 degrees and the core temperature is 15 million Celsius? I mean, there's so many places. That's the whole point of this tonight, right, is to talk about all those many places that are absolutely inhospitable for human life of any kind. The Earth is in a rare place. I shouldn't say that because we found many worlds that are in what we call the habitable zone. Okay, so we talk about when the universe is. It tries to kill us, but we also have to understand that the universe also provides almost like a template, building blocks of life. So it's just, yes, I'm here to hurt you. I'm here to unalive you. Okay. However, here's some building blocks of life. Enjoy. It's like, it's a schizophrenic universe, and it really is kind of weird because on one hand, it wants to kill you. On the other hand, it wants to provide you with life. It's kind of weird, isn't it?
It is.
Yeah.
But that's the balances of nature, I guess, right?
Yeah. But you got to understand, too, that on top of everything else, it spawns these extremely inhospitable worlds that are literally from the gates of hell itself. And then we also have the opposite end where the worlds are locked in permanent ice. Okay. Let's talk about Titan, Saturn's moon.
Wait. But in let's say our solar system.
Yes.
They're obviously going they're going around our planet. I mean, around our sun.
Yes.
Would it be possible for the Earth to be in the position it's in if not for these worlds that are so unhospitable, whatever? You know what I mean? For them to be in their position puts us in our position. So if they didn't exist, we wouldn't exist.
That's a good analogy, actually, because the sheep herder in our solar system is one particular planet. Do you know which one that is?
Which one, Jupiter or Venus?
No, Jupiter.
Okay.
Jupiter, the biggest planet in our solar system, the highest mass other than the sun. So Jupiter is the herald. It actually, reins in asteroid belt. It helps to keep the asteroids away from us. It also tends to create a balance in the solar system over time. You might say, but what about Saturn and Uranus and Neptune? Well, they're smaller than Jupiter, but they are still giants, but they're further out. So Jupiter is close enough to the inner solar system that it actually has an effect on what gets into the inner solar system and how it affects us. Now, interesting to note that we have Mercury, Venus, Earth, and Mars. Now, Venus is just to the inside of the beginning of our habitable zone. So it's just outside of it. Okay. And it has runaway greenhouse temperatures. The surface temperature on Venus, besides the pressure being 90 times higher than it is here.
Wow.
Okay. The surface temperature is over 900 degrees Fahrenheit on Venus' surface. Okay. So that's hot. And then you go out to Mars, and Mars is just inside the outer edge. So it's still considered habitable, but Mars is a frigid world. It doesn't have the same kind of solar energy striking it that our planet does. Okay. So, and the other thing is, Mars used to have a magnetic field. Our Earth has a magnetic field. That's very important. Magnetic fields are protective, they prevent high energy particles from getting to the planet's surface and going through you like a skewer.
Hmm.
Okay. Now, that's the thing that's interesting about these particles is they get to the Martian surface, and very, very high amounts of ultraviolet radiation make it to the sands of the Martian surface. And Mars used to have a lot of water, like Earth, except the Martian water, when it would evaporate, is H2O molecules, right? H2 hydrogens and one oxygen, H2O, evaporates into the air on Mars, which it had a very, very copious amount of. And then what happened was, as it would go into the air, that ultraviolet radiation getting through the waning or lessening magnetic field over the billions of years ended up breaking apart those water molecules. And the free oxygen went down into the ground, okay, where it ended up bonding with compounds in the ground, and the hydrogen left and took off into space. So over time, over billions of years, what happened was Mars had all of its oxygen that it used to have from the water disassociated from the water molecules, and that oxygen dove into the ground. And so the water content on Mars got less and less and less and less over time until we're where it is today. It's all locked up underground, hard as granite, as ice.
Wow.
And the oxygen that's in the ground bonded with iron compounds. And there's something that happens with iron compounds when they bond with oxygen, right? And you get a compound called rust. And that's why Mars is red.
Yeah, that makes
Why
sense.
it's red.
That makes total sense.
It rusted. And the actual compound is two iron atoms, Fe2. Fe is the iron indicator in the this iron symbol in the periodic table, and then O3, three oxygen atoms. So Fe2O3. So two irons, three oxygens bond together, rust. And known also as hematite, and Mars has hematite galore. Okay, so that can only form in the presence of water, of course. So Mars had an unbelievable amount of water in the past, but because its magnetic field died, when the water would evaporate, the water gets ripped apart, the molecules get ripped apart, hydrogen leaves, oxygen dives into the ground. Get that process going for a billion years, and your water's gone. The only water you have is the water that's left underground, but then that water freezes. And so now we have lots of water on Mars, lots and lots of water, but most of it is frozen. If it's very deep under the Martian surface, that water can still be liquid because of the pressure of the overlying rock strata pushing down, and it keeps the stuff down here liquid, okay, such as it is at the south pole of Mars. Our radar altimetry, that is radar imaging from an altitude, shows that there is a reservoir of water several miles in size underneath the Martian South Pole. And that Martian water reservoir is liquid water because the weight of the sediments overhead put enough pressure to allow it to be liquid. So you need pressure and you need temperature, right?
How deep would that be, though, Mark? Because if I'm thinking about if we were to colonize, would it make sense to drill into that source, or maybe would it make sense to develop some type of an underground colonization location so that you can easily, maybe not easily, but maybe tap into that source?
Well, the nice thing is that we don't have to get to that source to get water. And the reason is because in the mid latitudes on Mars, where you go up above 30, 40 degrees northern latitude toward the North Pole of Mars, there's ice sheets under the surface. Literally, you can blow away the dust and there's ice.
Wow.
So, and that's water ice and CO2 ice, and carbon dioxide ice. Now, but it's a mixture, and you can get both. And so you have water ice and dry ice, CO2 ice, on Mars. And so if you can find a CO2 pocket, you have dry ice for preserving anything, although the Martian cold is more than enough to do that. And then you have lots of water. Now, here's the other thing, though. We breathe oxygen, don't we? That's a problem. Mars doesn't have a lot of oxygen in the atmosphere. In fact, it has very little. It's 98% carbon dioxide.
Wow.
But what's carbon dioxide? Carbon atom, 2 oxygens. And engineers on the Earth set about to do a test. If we're going to send astronauts up there, we're going to have to be able to make our own oxygen. We can't do it by bringing giant tanks of oxygen because we're going to run out. So we'd have to make it. How are we going to make it? Guess what? There is a experimental package on the Perseverance rover. Remember that's just the one that's on Mars with the helicopter and everything? Ingenuity helicopter. Oh, yeah. I love that mission. It's fantastic. Well, there's a little tiny box on there about the size of a car battery. So it's about this big, maybe. And it's called MOXIE. And that's not just a cute name. It stands for Mars Oxygen In Situ Experiment, meaning let's make oxygen, folks. So this guy sucked in CO2 from the atmosphere and churned out oxygen that we breathe, O2. How about that? So now, and that's something the size of a car battery, right? It made enough oxygen to do whatever amount they said of work or for someone to survive. But if we're going to set up a habitat up there, and we'll do it robotically, okay, we'll probably make it, I call them inflatatats, basically an inflatable habitat. If we blew one of those up, we'd have to fill it with something. What are we filling it with? Are we going to fill it with the CO2 from the Martian atmosphere? Probably. Or we fill it with a very large MOXIE machine making oxygen. And that thing would run night and day forever. And you might have 2 or 3 backups to that one so that you always have it ready to go in case you need to take it offline for maintenance and get more oxygen from another side of things. So, so you basically will have all the oxygen you need. You'll have all the water you need. So what happens now? All right. And this, again, keep in mind, Mars.
So we're making an inhospitable world into a habitable one.
Only inside of a dome or a habitat, yes. And terraforming Mars would be a tough project, okay? But let's consider now that if you were to put all the oxygen you need and get all the water you need, great. Can you survive? No, not yet. No, you're going to need nitrogen for fertilizers. You're going to need growing, plots, to do that. And you'll have to do that inside your oxygen environment. So the nitrogen would have to be found either on the planet or brought with you to make a fertilizer patch. And then you would grow potatoes, tomatoes, rice, whatever, inside. And that is under the condition that the ultraviolet radiation striking the surface doesn't kill you or your garden, because ultraviolet radiation is one of those things in the universe that can wipe you out, right? And so what we want to do is mitigate that. We're going to stop that from happening. So how do we stop that? Well, we can do a couple things. We could shield our inflated tat with material that stops the UV dead in its tracks, yes, and we may do that. Another option is to bury the habitat.
That's what
put it underground.
Mm-hmm.
You were saying earlier.
Mm-hmm.
And if you bury the habitat, put it underground, guess what? Well, now you are shielded from the UV. Okay. However, then, and even before, there's a couple other things you're going to need if you're going to be on the surface, or either that or underground. You need heat. You're going to have to generate heat. So what do you do? I've heard people say, well, you just create a bunch of solar panels stored in batteries and run battery-powered heaters. Yeah, great idea. Except it may not work if you can't maintain those solar panels properly. You're going to have windshield wipers on them because the dust is like talcum powder. It settles on them, and you can watch the percentage drop when the Spirit and Opportunity rovers are on Mars. You saw all these photographs taken from Mars, and Spirit and Opportunity looked perfect when they first started. About 2 or 3 weeks in, Spirit looked like it had a haze of red on its surface, and Opportunity the same later. And That was because the dust from Mars is always in the atmosphere. The sky on Mars is like a salmon color. Okay, kind of like the red you see in my face and the lights around here. Okay, the sky is that color 24/7 because of high altitude dust always in the atmosphere, settling out and then being brought up into the atmosphere again. So you've always got dust falling on Mars. So you need to get rid of that.
But why not? But why not the possibilities of nuclear or fission, fusion, some type of a reactor?
Yeah. Well, Perseverance and Curiosity are powered by RTGs, radiothermal isotope generators, and the RTGs are effectively fueled, meaning they can run out nuclear reactors, and so they can generate heat, but a small amount of heat. So could you conceivably have these giant RTGs? Yeah, I guess so. Okay. The better option would be to have fusion reactors. And if we can make fusion reactors soon or some point, then that whole place will be effectively standalone because it'll have heat, water, air. Okay, the MOXIEs would be powered by the fusion reactor. So the oxygen in the atmosphere would be constantly replenished by the reactor. You'll have water, which would show up as ice and get melted by nuclear, the reactors, and there'll be a pipe exchange where the ice is melted and then purified and so forth. And then you only have to worry about the heating of the dome or the enclosure. And the way to do that, of course, is to make sure that you burn it, like the sand I was talking about, bury it, and that acts like insulation. So then you heat the interior, and you don't lose any of that to the outside much. Anyway, you don't lose a lot. So it has to be underground. We need to have reactors. We need to have oxygen. We need to have water. Okay, and then once it's warm enough, you can actually set up a growing plot and actually grow food. But guess what? You're not going to be able to do that when you get there. This has to be already underway before you even arrive. So the whole process has to be done robotically. And that's the thing that is good because it will save lots of lives. What if you go there and say, oh no, our inflatable habitat was hit by a meteorite? It's deflated-tat.
It's funny you say this because somebody in chat said, Mr. Django said, would it be possible to live on Mars like the movie The Martian? And in The Martian, it has where he's it's interesting you bring this up. I didn't mean to interrupt you, but somebody brought this up in chat. Go ahead. I'm sorry.
Yeah, that's Steven. I know Steven from Belgium. He's a great guy. Yeah, he's a regular with Sky Tour live stream. Hey, how you doing, Steve? Good to see you. Yeah, but the point being, we have to always guard against things that are trying to hurt us, and so it's important to understand, how life on Earth has protected itself. Well, it really hasn't done a good job. I mean, there have been millions upon millions upon millions of species that have gone extinct. And the reason is because they couldn't handle the conditions. What's that mean? It means that because our sun is spewing copious ultraviolet radiation all throughout its life, its existence, that has very likely been causing lots of mutations genetically, along with the other mutations that occur naturally in DNA. And so species A becomes species A-B and A-C and A-E, and each of those three subspecies that came from the original A will all be slightly different. And if the first one can meet the demands and be able to live through and succeed in the demands of this particular existence that was created, then it will continue and be able to reproduce and make more of itself, which is A-B. Okay. Now, if A-C, or so let's say A1, A2, and A3. So A1 might succeed. A2 may not actually be able to succeed because it's not responding well to the environmental changes. Maybe it got colder and it just didn't have that genetic capability to manage a way to warm its own self. And so A2 will die out over time. can't reproduce as much as say A1.
It sounds like something out of War of the Worlds. I'm just saying how we couldn't adapt to our environment.
Yeah. Okay. Yeah. That's right. I mean, well, keep in mind that evolution is, all about adaptation. It's mutation followed by adaptation.
Mm-hmm.
And so if A1 can adapt, it'll survive. If A2 can adapt, it may survive. If A3 can't adapt, it may reproduce maybe a couple generations, but then it will die out because over time it can't survive. So that's what evolution is. And that's something that happened here in spite of the fact that the Earth was trying to destroy us. Okay, we have tectonic plates. Tectonic plates are moving crustal plates, and at the boundaries, we got many volcanoes. Volcanic eruptions have destroyed people's lives and have actually ruined animals and destroyed animals throughout history. Okay, the Great Permian extinction 252 million years ago was a volcanic eruption, it seems. And this volcanic eruption threw billions and billions and, like Carl Sagan, billions and billions of tons of carbon dioxide into the atmosphere. It rose, the temperature on Earth rose 21 degrees in just a few short weeks.
Wow.
And that was more than any creatures in the ocean could handle, and that was more than land animals. So 96% of all life on this planet died. 96% from a volcanic eruption.
Wow.
Now, you think about that and you say, wow, yet here we are.
You just scared me, Mark. You really just scared me.
Oh, it's not over.
Oh,
really?
Come on, my gosh. Everybody talks about the super volcanoes and everything
else. It's not over.
Go ahead. I'm sorry.
Got to get them back somehow. Anyway, so the bottom line is that when you talk about, like, for instance, a volcanic eruption that wiped out their life, well, at that time, the creatures that would become us, mammals, were rising to dominance. But unfortunately, this Permian period extinction wiped them out. And many of them, there were still some survivors, but they basically retreated. And there were other animals to fill those empty niches right away. And those animals were dinosaurs because they loved the heat. And so we saw that's when the age of the dinosaurs began, was after that major extinction event. Had that not occurred, I don't know that we'd have dinosaurs. Maybe. So the dinosaurs then, they ruled for 150 million years or so. And then what happened? Well, then the dinosaurs were rendered extinct by an impact that cooled the planet again. Right? And blocked the light going to plants that the plant-eating dinosaurs would eat. And if the plant-eating dinosaurs died, well, then the meat eaters would come along. Hey, where's my food? And they have nothing. Okay? So the plant-eating dinosaurs fell first. The meat-eating dinosaurs shortly thereafter. Plants were sacrificed almost immediately because they lost light. And they didn't have any way to further their existence. So that process led to a domino and a catastrophic set of extinctions again. 76% of all life on the planet died at that point. Now, who do you think was hiding in the wings waiting to come out? Well, those darn little mammal things that were about to be mammals. Now, the planet was cooling off again, and they could handle it, and they just rose up and filled those niches. And next thing you know, we have hominids. We have Lucy, Australopithecus afarensis, right? 4.2 or so million years ago in Olduvai Gorge in Africa. And so, we ended up having that happen. And we are here exactly the way we are because of a curious set of circumstances. And those are two major extinction events. There were 5 on this planet. 5. And so the Permian, and then several others, and then this one here that I'm talking about 65 million years ago. The asteroid that struck off the Yucatan. Sure. It's known as the Chicxulub impact. It's known as the KT boundary event. It's known as the asteroid that killed the dinosaurs, right? Obviously. Depends what your specialty is. If you're a geologic guy, you're going to say KT boundary event, right? Whatever. Anyway, all that said, you can see that life just tenaciously held on and found its way through all that. But you know, that's because we had a star that fostered that potential. And I believe the universe fosters life. I mean, it does. The same universe is trying to destroy us is the universe that's saying, here, I'm going to destroy you, but here's some life. Here's some building blocks of life. And so on our planet, we started as a molten mass of boiling magma. The entire 8,000-mile globe of this planet was molten magma, all a magma ocean, giant magma ocean. And as it cools into solid rock, right? But then you have earthquakes and tectonic plates breaking it apart, more eruptions, more magma, impacts all over the place, brought down to magma again. And then one major impact by a Mars-sized body on the early Earth. And that blew a giant chunk out of the Earth, which started to make like a ring around the Earth, which coalesced over time to become the moon. You got it. And then give him a star, give him a cookie. and then that the moon, in fact, orbited the Earth. It was much closer initially. I mean, it was so close that the day on Earth was only 4 hours long. And as the moon was orbiting Earth, it would be spiraling slowly away, which it's still doing to this day. And as it spirals slowly away, it's robbing a little of the rotational energy of the Earth with its gravity. Okay. And so that robbing, okay, that thievery slows the Earth down. So instead of spinning rapidly to make a 4-hour day, it started to slow down, made a 16-hour day, 18-hour day to where it is today, making a 23-hour, 56-minute day.
So wait a second. Wait. Time out. Are we going to eventually need 2 leap years?
I don't know about that.
Because
Okay.
if it's slowing down, I mean, eventually, is it going to be where we have to extend it again?
No. See, eventually, if the sun would live this long, eventually we will be tidally locked to the moon as well. So someone on the other side of the Earth or wherever is going to end up, wherever, maybe even here, our location, wherever, is going to see the moon in the same spot in the sky all night long because we're going to be tidally locked. We're going to rotate at the same rate, just like Pluto and Charon, its moon, are. The Pluto and its moon Charon are locked to each other. They show the same face to each other.
So you're telling me some people will be able to see the moon, some won't, because it's going to be tidally locked?
That's right. At some point. However, just to let you know, probably not going to happen because the theoretical time it's going to take for that to happen is a number of billions of years, more billions of years than the sun has left to exist. Okay. Yeah. So we're not gonna see that. We're not gonna see.
What would you say right now as far as physical threats? Like I wouldn't even say it like that. Natural phenomenon threats. Is it going to be earthquakes, volcanoes? Is it going to be the sun? Is it going to be something from out there that is the biggest threat? What would you all of the above? It's
excuse me. It's always all of the above. Okay, because we are not on what we call a super habitable world. I'm going to tell you right now, we're not super habitable. We're a world that is habitable, but not super habitable. It has dangers. We have tectonic plates. We have earthquakes. We have hurricanes. We have tornadoes. We have tsunamis. We have cold. We have hot. Heat. So this is not super habitable. If the Earth was just up and down in its orbit and didn't have climate change, okay, it didn't have a winter, it didn't have autumn, spring, and fall, then we go around the sun like this, and the equator would always be a certain temperature. The mid-latitudes where you and I are would always be a certain temperature. Never change. There'd be no winter, really, except up at the top, and it would always be winter, okay? So it would change drastically, and for all we know, that tilt that the Earth's axis has, which may have occurred from that major collision with that Mars-sized object, may have sealed our fate as a world that could be habitable to some extent. We don't know. Because if it stayed like this, you might say, oh, but then everything would be stable. Yeah, that's true. But guess what? There might not be as much diversity of life because the life and the diversity of life depends on changes that have to be responded to environmentally. So creatures, oh no, it's getting cold. We better figure out how to stay warm. Okay? The creatures that could figure out how to stay warm survived. The ones that didn't died. And so the creatures that stayed warm were able to propagate and proliferate again. And then, of course, the normal mutations occurred, and then those next lines came out, and now they already know how to handle the cold, but then they have different characteristics that either were selected to continue or not selected to continue. And it just, and just because we label evolution what it is doesn't mean it's stopped. It's still happening. I have a talk I do that talks about all the many different creatures still evolving on our planet, and maybe we'll do that as a show at some point. The evolution is obvious, from across generations. You can actually see, and it's kind of neat, So now, as far as other worlds, okay, there are some other things that we have to understand about other worlds.
Want to hold that thought before we go to break?
Oh, we do have to go to break, don't we?
Yes. But it's funny.
We do.
I was thinking about that when you just mentioned that, and we'll bring it up. But my question to you, maybe coming back from the break, is you said you spoke about mutations that life has happened here on our planet, different various types. What about us going to an exoplanet, even though the conditions might be right, but will we be able to adapt to those environments based on the mutations that happen on that planet naturally? Can we adapt and adjust to that environment? Because we're not from that planet. See, we're from here. We've adapted over time. But just to go into a new exoplanet, is that going to be as easy as people make it sound? That's the question. I want to see if you can answer that, Mark, when we come back. But
all right,
take a break. So why don't we?
Right. We'll be right back. I can answer that. Shh! Don't tell them.
All right, we'll
be right back.
Here we go.
Field is changing, and now more than ever it's time for professionals to lead the way. Join the Oz Professional Paranormal Investigators Association, a global network of serious investigators dedicated to raising the standard of real paranormal research. Access professional certifications, advanced training, and courses exploring true investigation, psychic phenomena. If you're a real paranormal investigator, be a part of the group defining the future. Join today. Visit ozinstitute.org. That's ozinstitute.org. The new book, How to Research a Haunted House by paranormal investigator Margie Kay and professional researcher Violet Wisdom, is now available from Unex Media. This one-of-a-kind book explains how to do research on a house with uncommon methods and resources used by historic home researchers, and how to determine who may be doing the haunting and why. How to research a haunted house can be used by homeowners, renters, investors, and it should be in the library of all professional paranormal investigators. Get this unique book at unexmedia.com or amazon.com. That's unexmedia.com or amazon.com.
Hey, welcome back. And oh, Bill's still here. Oh well.
Also,
I,
make sure to check out the unexplainednetwork.com or unexnetwork.com when you get a
yeah,
chance. All the great
yeah,
programming as well there.
yeah. I mean, we used to be on another network, but turns out this network much more responsive. So I'm very pleased to be here, and I want to thank Race for inviting me and Margie for inviting me to be here. It's very nice. I enjoy
Me
it very
too.
much. Yeah, I was gonna get to you.
Uh,
All right. So before the break, you asked a question that was very interesting. It's like, what if we went to another planet, and would these sequence of evolution be interrupted in any way? Actually, I kind of made light of it, kind of smirked a little bit, but the fact is that's actually a very intelligent question. Don't let it go to your head. Okay.
I'm usually the
Um,
one that asks when you say there's no such thing as a stupid
well,
question.
no, there isn't, and that's true. And so, in all seriousness, so we're used to the environmental pressures created on our planet by our sun and by the activity that occurs on our planet. But if we go to another world, then we have to consider long-term consequences. By the way, it's a long-term longevity of the human race on another world that we care about. If we go to another world and we see what's going on and we say, "Hey, this is a nicer place," maybe it's a super habitable world, a world where it's much easier for human species to survive because our DNA is structured in such a way that we're just basically we have all these checks and balances built into our DNA to counter virus attacks and other things that happen to us. Um, just the way we heal. What if that's something that is somewhat unique to humans because it was born out of how we evolved on planet Earth over time? So the nature of how our bodies efficiently breathe oxygen, the nature of how our body heals when it's injured, all that is on Earth. It's built into our system. Okay, how long our heart will beat, and how much oxygen we can extract from the air when we breathe. Well, what if we're in another world, and as we evolve on another world, say we go 30 generations on another world, the ones that arrive will probably say, "Hey, this was great," but the ones after 30 generations, maybe more, might actually have changed dramatically because they may actually be a group of people that now have qualities that they could never possibly have on Earth, all because of the way the new planet presented its obstacles to evolution to them. And if there were fewer obstacles, oh wow! So look out! I mean, now we're talking about a new group of people that are literally exploding evolutionarily in a lot of different ways. So it could hurt us, it could help us, and if it's harder to live on than the earth, well then we're going to have a tough time.
Mm.
But if it's more habitable than the earth, then our intrinsic natures are going to have a much easier time, and that's going to change a lot of things psychologically, physically. So I do think that exoplanets will have their own challenges they offer the human race, both positive and negative.
Question though, with science progressing the way it is, would be there be an ability maybe to genetically alter humans to better adapt in a new environment?
Well, we do that now, and things
Right.
called vaccines and penicillin, and so obviously we're adapting in a germ-filled environment, right? Well, if there's a virus that occurs on another planet, and our existing immune system can just easily shrug it off, then we may never get sick. There's a huge change right there. We may never ever get sick on another planet, for all we know. So that's interesting because that will foster a much more healthy species, much more healthy development, less attrition to disease. All right. So already you can see how the evolution on another world would be changed by the nature of that world. You know, Spock, first life here. Let's not tamper with it, right? Come on, we want to make sure that we don't mess too much with ourselves before we actually figure out whether the other world is something that can support us without having to mess with ourselves.
Because
Follow?
also we have to survive. It's also about the water, the food supply,
Yeah, yeah.
everything else. I mean, we're going to have to adapt to that as well. I mean, a burger here might not taste like a burger over there.
Oh, I'm pretty sure that it won't.
You
Okay.
know what I mean, though? And I'm just joking, but
I know what you mean. I do know. Yeah. And so that's the other thing. We have to adapt to new foods and new methods to produce food. Maybe it'll be easier. Maybe it'll be harder. Maybe it'll be impossible. Maybe it'll be easier than we ever imagined. You know, so we don't have that information.
We don't have a
think
choice.
it's interesting.
We don't.
Oh no, we
got to go off world because this becomes an uninhabitable.
We gotta go before 5 billion years elapses. Yeah, because the sun is gonna go extinct after 5 billion years. Okay, so 5 billion years, not 500 years. Don't go off and don't say that. Okay, after 5 billion years, the sun's going to change, and it's going to change for the worse for human life. And that leads to my next discussion about how the universe tries to unalive us. Okay. And that is, I'm trying.
You are trying.
I don't go for that. I don't go for that politically correct crap. I really don't. Okay. The universe tries to do that to us, tries to extinct us in a variety of ways. And we have to look at the stars. Now, the stars themselves are fascinating objects. They're orbs, hot gas, right? But tell me, Mark, what do these stars consist of? How are they actually made? What do they, how do we classify them, and that's something that we have to understand. So one thing we have to look at, how are stars defined? Well, they're defined by their temperature. Okay. They're defined by processes they use to make energy. Okay. And they're also defined by the size that they have. And that's related to how luminous they are. They're the bigger they are in diameter, the more bright they are in our sky. All right. So we have characteristics called luminosity to describe that bigness of a star, the intrinsic brightness. And we encapsulate those characteristics into two main parameters, and that's spectral class and luminosity class. And when Henry Norris Russell and Egnar Hertzsprung graphed stars with those different characteristics, they found something very interesting. And this is what they found. Okay. Let me see if I can fix this here. I guess I can't. Okay. Well, you can see it. Okay. This diagram right here. Okay. If you look right up here, you'll see these are the hottest, bluest stars in the universe. These are O stars. Okay. And you can see down along the bottom, you see that it says O at the bottom there, and it goes across BAFGKM. Those O stars are the hottest and bluest that the universe has. Okay. And those stars are so bright and so hot that they will basically run out of all their nuclear fuel in just a few million years. And so when they do, guess what happens? They explode. Okay. Because they have nowhere else to go. And that's a whole nother talk. Okay. Then we have the B stars. The B stars last a little bit longer, but again, notice again that snaky line right there that goes down from the O all the way up there, all the way down to the bottom to the M's. Notice it's like a line. Okay. When they plotted stars that are fusing to make energy, fusing hydrogen into helium, that we call those normal stars. Well, they called that a dwarf. Okay. Not a white dwarf, but a dwarf star. And not that stars are dwarfs, because they're not, because these O stars up here, these suckers are really, really, really big. Rigel's a massive star, and it's really, really big star. You can see there at the upper right there, you can kind of see Deneb, you see Rigel right below it on the lower left. Okay. So these stars are massive, giant stars up in the top there. But when you look at right on this line, snaky line, those are stars that are more massive than the sun, but not absolutely so massive that they would, if you replace the sun with them, they go all the way out to like Mars or whatever. Okay. That's not what that is. Okay. But see, it does make me blurry. So then when you get to the A stars have a slightly different color. The A stars are more of a whitish, bluish color. Okay. Okay. Vega, for instance, is an A star. It's the quintessential A star. within each of the with each of the classifications, we have 0 through 9. So an O0 is the hottest and bluest star that the universe has to offer. That's a normal star. Vega is an A0, so it's the hottest and whitest, bluest star that the A category can have.
But do their lifespans expand as it goes down this line?
Yes, it does.
Okay.
That's what I was getting to next, of course. Okay. So as you look at these stars, the O stars are millions of years. B stars last a few more millions of years. A stars can last hundreds of millions of years, okay, or more. And then we have the F stars, which are starting to turn like a yellowish color. And those stars last longer. The G stars are like the sun. Our sun is not a G0, not a G6. It's a G2, number 2. Okay. And so we're just right there at the very beginning of the G category. And that's a 10 billion year lifespan for a star like that.
Wow.
Now, you keep going down the list, you have K stars, which are this markedly orange, and then M stars, which are very, very red. Now, they get small in diameter when you go down on this. This is called the main sequence, this main line here. Okay. It makes more sense to talk about Jupiter and its moons when you're talking about M stars and their planets. Okay. Because M stars and their planets, okay, the planets are all orbiting very close to the star, kind of like Jupiter's moons orbit close to Jupiter. Okay. Which is really interesting here. So when you look at these M stars down there, okay, these M stars are sometimes half the size, a tenth the size, or a 50th the size of the sun, okay, in mass. Very, very small. Sometimes there's even an M star that's been found that's a little bit smaller than Jupiter itself, okay, but it has 80 times more mass than Jupiter, so it can be a star, at least. So, and it's the M stars down there, okay, that have the longest lives of any star in the entire universe.
But they're cooler, though, right, Mark?
They are. And not only that, M stars have more planets around them than any other type of stellar classification that we see here. Wow. Okay, any other. Okay, so we're looking at, the O stars, no planets, because the formation processes, it's so violent that they could not allow it for a planet to coalesce in any region near them. Then the B stars, similar. The A stars, we can have a planet around an A star, depends on how the star was formed and where it formed. Okay, so when you get to A and beyond, now we see more planets. And so at the M star level again, those are the smallest in diameter, smallest mass, lowest temperature stars. What's low temperature? About 5,000 Fahrenheit on the surface. Our sun's 10,000 Fahrenheit. Now, that 5,000 Fahrenheit little tiny star, okay, may have 5, 6, 8 planets around it. All right. And if you want to talk about stars that are that small with that little energy and whether they're going to have planets around them, then, as I said, we talk about how Jupiter looks compared to its moons rather than the sun and its planets. Because every one of those planets around one of those little M stars down there, every one of those planets is going to be very close to the star. And some of those planets might be actually in the habitable zone where life could exist and water could exist.
What is the life expectancy on one of these M-class stars?
See, again, a point that I was going to make, but that's fine. It's okay. I can bring it up because
the reason I say that, because wouldn't be this kind of a star with the proximity of the planets to it be the prime candidate for one that we would look for?
Yeah, we are. In fact, and we there's more planets around those stars, those M stars, than any other kind of planet, because there's more M stars in the universe than any other kind of star. So they're the most populous type of star in the entire universe. There's more of them than any other kind. And
wow.
And that's the normal stars. Now, as far as their lifespans, the question you asked, okay, the universe is 13.8 billion years old. Okay. The first M star that was ever created is still going.
Wow.
Yeah, because they don't live billions of years; they live trillions of years.
Wow. That
There's a
is
reason for, yeah, it's crazy, but there's reasons for that, and it's because when M stars are generally in a star like the sun, we have hydrogen in the core, all right, and the core is where the fusion's occurring. It's all in there. All the stuff in the outside of the sun is just along for the ride, and that core represents about 15 to 20% of the entire size of the sun. Just 15 to 20%. Okay, so that's the only place. And hydrogen from out here, the rest of the star is made of hydrogen, which is fuel, but it can't get into the core, and there's nothing to bring it there. So that hydrogen in the core is all there is for the star to continue sustaining itself. All right, but in an M star, it's interesting because in an M star you have the core, but then there's this giant envelope of hydrogen, just like in our star. But in our star, we have radiation pushing out. It's called a radiative envelope, a part of the radiation part of the envelope. And that radiation goes out to, outside of the star. And on that outer area, there's like a boiling pot material, like a convective zone of stuff that circulates and does that. But that's on the outer shell, little thin outer shell on the sun. Okay. But in the M stars, the entire star is doing that. So it's dredging up hydrogen from the surface of the star and bringing it down to the core. So the star has endless hydrogen to fuse. And so that's why they live for trillions of years and not just billions of years. Okay, because it has what's called a full convective envelope, for those that want to know. Okay, so that stuff's interesting. So we classify stars like this. Now, we talk about the main sequence, and those are a type 5, Roman numeral 5. We say that's a dwarf. So our sun's full spectral type is made up of its spectral class, which is G, and its luminosity class, which is a Roman numeral 5, okay, a V. Okay, and that Roman numeral 5 means normal hydrogen burning star. It's going to be in that main sequence thing you see there, snaking down the middle. Okay, now when you run out of hydrogen, well, now you're going to leave the main sequence behind, because now you're going to start making other elements that we find in that ugly periodic table. Remember this? The periodic table, nasty. Okay, yeah. Well, that periodic table is ugly, nasty, and gross, and we don't want to look at it. Okay, hopefully we'll see a little bit. Anyway, but the periodic table elements are all made in the hearts of stars, almost all. There's some that are synthesized in labs and stuff, but most of them are made in stars. And so when we look at this snaky line, we can expect that the stars here are making hydrogen into helium. Okay, and then once they stop making hydrogen into helium, they're no longer on that snaky line, because those are what we call normal stars, or dwarfs, the type 5 Roman numeral 5 luminosity class stars. Okay, however, that's what we see there. Now, if we have run out of hydrogen, what do? Well, that means we have all this helium in the core of the star, and that helium ends up being fused into things like carbon. How does that happen? Well, it happens when the star leaves that middle snaky line. And if you look at the upper right there, you can see in the upper right, we got stars like Pollux, Aldebaran, Arcturus, okay? And those are the giants, all right? They have begun to fuse other elements other than hydrogen into helium. Now they're doing helium into carbon, maybe carbon into oxygen. And then up top, we have the supermassive stars like Betelgeuse and Antares, okay? And Antares, the eye of the scorpion, Betelgeuse, the upper left star in Orion, okay? These stars evolved from this branch up here, right here. These are up here, and they were bright, hot, and blue at some point in their history. And once they evolved and they started to grow in size, when they started fusing other elements, okay, as they grew in size, that outer envelope, which was closer to the hot star's core in the beginning, got further away from the hot star's core. Cool. And when it got cooler as it went out, and then turned more red. So it's like white hot, okay, as a white hot object starts to cool, okay, it goes from white hot, or blue hot even, it goes to white hot, and then it turns sort of a yellow, then orange, then a dull red, right? Well, as things cool down, they turn more red. And so stars are the same. As the star expands in size, those outer areas are so far from the hot core of the star that they are cool. And
so are you telling me that went from an O to an M?
That's correct. That's exactly right. And because the bottom scale there, right down here, this is actually driven by temperature.
Right.
So, okay, when you see a star that's an O star, okay, and it's say 40,000 Kelvin, okay, Kelvin's a absolute scale, starts at 0 and goes up, right? It doesn't have negative numbers. So if you have a star that's 40,000 Kelvin, you can tell that's a really hot star, okay? And if you have a star that is 5,000 Kelvin, you know that's a lot less. A 40,000 Kelvin star is going to be blue, hot blue. A 5,000 Kelvin is still hot, still burn you to a cinder, but it's red because it's cooler than the 40,000. By contrast, it's cool. In fact, if you put a little tiny M star in front of an O star, right? The little M star, which would glow all its own in the middle of space, would look black against it because the O star would totally wipe out the dull red glow coming from it.
Right.
So this is how we classify stars. We have a spectral class and we have a luminosity class here, and we measure that by how many times luminosity of the sun. Notice right here we have
fascinating. That is really fascinating.
See, we have a 1, and the 1 is the sun. So if you go over, you'll see the sun there.
So we went from a star that could survive for a few 100 million to a trillion.
That's right. That's right. It's a fascinating universe with a lot of variation out there. And this is why does it do that? Okay. And apparently my camera can't survive this long. You know?
Wow, maybe take the image down. It might. I don't know if that's. I don't know what's going on.
It's not. But it's okay because we're done with it anyway. All right. So
wait, before you continue, if it's a supergiant, that means the stars, even though it's giving that much heat, the 5,000, it still doesn't have to be as close because it's larger in size. So the planets don't have to be as close, right?
Well, let's talk about that. Let's talk about other ways that the universe wants to destroy us. When our sun runs out of hydrogen, here's what happens, okay, which I didn't tell you about, but this is fine. We can talk about this. This is the best part. Okay, when our sun runs out of hydrogen, what's going to happen is the core of the sun is going to start to collapse a little bit, because what happens is as it's producing helium and it's making this radiation pressure pushing outward, and that radiation pressure pushing outward is balancing the gravitational collapsing force is trying to collapse it. So those forces balance. Those are called hydrostatic equilibrium balance point, okay? And so when you have this equilibrium, the star is pushing out with as much force as it's trying to collapse. Now, when I say collapse, I mean gravitationally, because all that mass is trying to collapse to the center. That's how stars work, right? I mean, we have all that collapse. So the reason stars light up at all is because you have this really, really hot center because of all the pressure of all this material on top. And as it does that, the temperature heats up in the center, reaches a certain critical point. And at one point or another, boom, it winks on, and now it's burning hydrogen into helium, and we have a star. Okay, so when that happens, we have this period of time while the star is on the main sequence when it's making hydrogen into helium. And when it does that, it's actually pushing out with as much radiation pressure as gravity is pushing down and trying to collapse. So the star stays stable. But as soon as it runs out of hydrogen, guess what wins? Gravity. And the star begins to collapse. The core begins to collapse. And as the core begins to collapse, all that pressure from all that mass out there, as the core is collapsing, heats up the core. And if the core reaches 100 million Celsius, okay, or 100 million Celsius, then the core can start fusing that helium that was made by the hydrogen and make it into carbon. And that means that's further down that nasty periodic table, okay, that we saw that. So you see the hydrogen is on the upper left underneath the skytourlive.org. On the right, you see the helium, okay? Well, that helium would end up fusing to form some carbon. And there's, you have lithium, beryllium, and boron in there as well. Okay, but those are quickly surpassed, and you're left with the more useful carbon. Okay, now keep in mind that carbon that we're looking at there that gets formed, carbon is the fourth most abundant element in the universe. You're made of carbon. Every atom in your body was once made in a star. Isn't that crazy?
Mm-hmm.
So when Carl Sagan actually said, "We are star stuff," it was true. We are made of stars. We are star stuff. Okay. And the thing that's interesting too is that that carbon, all right, now that this helium's fusing into carbon, the star begins to grow. And so the outer areas of the outer regions of the star expand rapidly, and we get this massive envelope around a very hot core. The core is the only thing fusing anything, but this massive envelope that's along for the ride. Just like in our star, we have a tiny core in our star with a massive envelope of hydrogen that's just along for the ride.
Does it cool? Does it cool while it's doing that?
As it expands, it's cooling.
Okay.
Yeah. So it's really hot in the middle, and as it goes out, it gets cooler and cooler and cooler until it gets so chill out here, okay, that you can actually get molecules to form out there on a star. Keep in mind that in the surface of our star, okay, there's no molecules, there's no atoms. It's all atomic nuclei. We call it plasma. The electrons are torn off because of the energy that they absorb from around them. And so all you have are atomic nuclei in our star. Free protons, free electrons, all running around doing stuff. Okay? That's all we got, right? But in a giant star like that, where you have this red giant now with all this material out there, out here, the temperature might be cool enough so that atoms can reform. And so that you can actually get a situation where you have molecules of multiple atoms form. So you could have carbon molecules formed out there that become very large pieces of dust. Okay. And indeed, we see that there are some red giant stars that are something called carbon stars. They have literally an atmosphere on the outside of what is like almost soot. It's just carbon. And so the stars are a deep red. They're literally almost, they look like little jewels. Now, we look at carbon stars and Sky Tour live stream quite a bit. We actually will go and bring them up and show people the stars that are really this deep red color. And they look very different from normal red stars. They look very different from Betelgeuse. Betelgeuse is orange, but you've never seen an extremely deep red star before until you've seen these, carbon stars. So we see that stuff. So now we're talking about these stars expand. Now, wait, what's that mean for Earth? Well, as I said, the universe is trying to destroy us, okay, every way it can. So when our sun runs out of hydrogen, its core is going to collapse. That core collapse is going to heat it up tremendously, and we're going to have that big envelope of our sun starting to expand. Well, how much is it going to expand? It'll almost certainly envelop all of Mercury, okay, and it'll burn Mercury to a cinder. It'll probably envelop Venus and burn it to a cinder. And it may also possibly envelop the Earth and burn it to a cinder.
Wow.
So everything we've ever known, all of our history as humans, all of our architectural and archaeological sites, all of that will be lost forever.
I can't even comprehend the size of the sun as it is now, expanding to that size that it actually encompasses the Earth.
I know.
And the
Well,
other planets and closer.
and it's even better than that because the sun is a relatively moderate-sized star. It's not even a big star. There are stars so much bigger than the sun that it would just make your head spin, okay?
Like how much bigger?
Well, let's see.
10 times, 100 times?
Oh, yeah. We have stars that are 1,000 times bigger than the sun easily, okay? And I think I can give you the exact name. I'm going to get that exact number for you here because I know what the star is. And
while you're looking for that, obviously they're probably cooler, right? In these sizes.
Yeah, exactly. So here's the thing. Okay, the star I'm talking about is a star that's located in the constellation of Scutum, Scutum. Okay, not the other thing. I mean, there's a lot of people out there making jokes already. I know,
I
but
can hear it.
yeah, Scutum. Okay, he said no, I didn't. Okay, U Y, letter U, letter Y, Scutum, and that star is 1,700 times the radius of our sun. And now think of that as a sphere, okay? Right? Now, that's the radius, 1,700 times the radius of our sun. Okay, what about the diameter? What's the diameter of a star? 2 times the radius, isn't it? Okay, so now you can see that this star is thousands of times bigger than our sun. Okay, and it is such a massive object. Okay, you could put around 5 billion with a B, as in boy, 5 billion suns inside of it.
Oh my gosh.
Now, talk about blowing up your brain. Okay, but that's incredible. But there's something to understand. Remember, I talked about as the stars expand into these red supergiants, right? They get lower in temperature, right? Well, there's something else they do as well. They get lower in density. If you have a compact star, it's very, very compact. It's going to be pretty dense in there. Okay. But as it expands, that same amount of material expanding outward, well, to get that much material in a bigger sphere, it's going to become less dense. So it's quite possible that in a star like that, you could sort of fly through the outer layers and not even realize you're in the star, because it might actually be, well, the temperature's rising on the hull, but I don't see anything. I mean, I see the star way over there, and it looks like a bright spot because you're looking at the core, okay? But you might be inside this very tenuous, dispersed envelope of the star, okay? But it's still 1,700 times the radius of our sun. And that's a star. And so, but that material on the outside, see, because of that, you can get all these beautiful molecules forming out there. And then once the star goes supernova, which it will, all that stuff is going to go shooting out. Another way the universe would like to kill us, right, and destroy us is by creating a supernova. And that material is going to come out at like 30,000 kilometers per second when that happens. And at 30,000 kilometers per second, how fast is that? Well, that's about the fastest that mass can move in the whole universe. That's one of the fastest speeds that mass moves in the universe.
But does it have the density to destroy whatever's in its path?
Well, not like a snowplow, but anything moving that fast is going to have a lot of heat associated with it. So if it passes over the Earth, it would rake all the atmosphere right off our planet. Okay. Now, at that speed, 30,000 kilometers per second, you know how long it would take you to get to the moon? 12 seconds.
Wow.
Yeah. And that's one of the fastest speeds in the known universe is a supernova expansion.
So okay. I guess it'd be over pretty quick.
Well, I guess, yeah. I mean, you know.
I wouldn't want to be here, but I'm saying it's going to happen so fast.
But our star's not going to go supernova. Okay, it's going to not have that. Okay, only massive stars go supernova. Our sun is going to suffer a much more quiet death. Okay, it's going to swell into a red giant and just slowly eat Mercury, slowly eat Venus, and slowly eat the Earth. That's how it's going to happen. So see,
why is it that the case for our sun?
Because our sun is not big enough to actually go supernova. What will happen is our sun's going to turn into a red giant, and it may fuse some of the helium into carbon a little bit, but mostly it won't. And what will end up happening is it'll go to a red giant, and then instead of blowing up, it's going to start to shrink again and shrink down to a white dwarf. The next thing that wants to destroy us in the universe.
Oh my God, Mark. You could make me have dreams tonight like somebody else had in chat tonight. Oh my gosh, dude. So what happens at that point?
Well, with white dwarfs?
Uh-huh.
Oh, well, the white dwarfs are interesting because when you talk about a white dwarf, one of the things to keep in mind is that these are the remnants of low to medium mass stars. They're the remnants of stars like our sun. Okay. And white dwarfs are kind of cool. In fact, in my in this title page, you can see there's a white dwarf in the lower right corner there. Okay, that I put in there. And then, but the other thing about white dwarfs is their composition. These white dwarfs, they're stars. We call them white dwarf stars, but they're not fusing anything. See, here's what happens. After the star expands into a red giant, okay, the star begins to go through these thermal pulses where it puffs off its outer layers. And all that's left is the core in the center. And as that core is no longer doing any fusion, it starts to shrink and shrink and shrink. And it gets compressed by the gravity trying to literally crush it out of existence. But it can only go so far. Okay, and this is what a white dwarf looks like inside. Okay, now I don't know how to get this to work right, but let's see here. I don't know. I can't put this up there without.
Yeah, it's going to automatically resize. Yeah.
Yeah. Okay. Anyway, so the white dwarfs have this hydrogen on the outside, which is expected because that's what a star is made of mostly. Then it has this helium shell on the inside because hydrogen made into helium, and then it has this weird carbon and oxygen interior. If it's a star that's a little more massive than our sun, okay, and this is weird because I know the cross section looks kind of weird, but this is what a white dwarf is. Now, the thing about the white dwarfs is when they're first formed, okay, they're as the star collapsed. Let me take this off for a minute so I can illustrate. When the star collapsed, all right, it actually ended up creating a compressed star in the middle, the compressed core. But it collapses and collapses and collapses, but it can't go beyond a certain amount. That certain amount is
Did it solidify though, Mark? Because it looks like just based on what I just seen in the illustration, the carbon oxygen, is that more of a solid core now?
It's a crystallizing carbon oxygen core. Okay, so it's a very strange material, yes. Okay. But what's happened is as it collapses, it's compressing and compressing, but can only go so far. And the reason it can only go so far is because of this particular limit called the Chandrasekhar limit. Now, with stars of a certain mass, all right, if the remaining core that's left behind is less than 1.44 solar masses, yes, it's that specific, then the star will collapse and stop collapsing at white dwarf stage. Now, why does it stop? Because of something called electron degeneracy pressure. Wait, what? Okay. Here's a checkerboard. You put a checkerboard in front of you, and it's got all these squares. Put an electron in each one of those squares. So now I have a checkerboard full of electrons in each square, one electron in each square. No two electrons can occupy one square. That's what's happening on this star. The electrons are being squished together so much that all those squares are filled. And so they push back. And they push back with enough pressure to hold that star from collapsing further. Now, there's nothing fusing anymore. This is the latent heat of hundreds of millions of degrees in the core left from this star's death. And so it'll take probably longer. Well, it takes many tens of billions of years for these things to cool to a theoretical black dwarf from a white dwarf. Okay. But we've taken pictures of these wonderful planetary nebulae, which are the outer mass of these stars that have thrown off their red giant envelopes. The Helix Nebula is an example. The Ring Nebula is an example. The Dumbbell Nebula is an example. Okay, we've captured a lot of these with Sky Tour live stream and shown them to you. And what happens is those gases are now glowing. Why are they glowing? Because the white dwarf is so hot, it's giving off most of its energy in the ultraviolet. And that ultraviolet will heat up and cause the atoms in that outer envelope that formed back again when it was cooler to actually ionize, meaning the electrons leave the atom for a period of time. As they leave the atom, they're gaining energy. The ultraviolet energy is taken by the electron. Then they give it up when they fall back in. They give it up in the form of light. So hydrogen will glow predominantly red. Oxygen will glow predominantly teal, green, blue. Okay. And we see that in these nebulae, which is kind of cool, And so
I got to ask a question. I'm sorry. And it might sound stupid, but in comparison to its original size, how much smaller is the white dwarf from its original size? And is it hotter than it originally began?
The answer to the second question is absolutely. Okay, now here is how big it is. All right, when we talk about a white dwarf, the size of a white dwarf, we have to understand that this was a massive star.
Right.
Okay, our sun was 865,000 miles across, right? Okay, when it becomes a white dwarf, all right, the envelope will be gone, but only the core will be left. And that's going to shrink down to about the size of the Earth.
Wow.
Yeah, the Earth. Wow. Yeah, little tiny dot next to the sun. Yeah, right. That's how compressed it's going to get.
Here's my next question. What is the lifespan? There's a reason I'm going with this. What is the lifespan of a white dwarf?
Lifespan of the white dwarf. Well, first of all, the star's already dead. This is just a stellar remnant, we'll call it. Okay,
but it's still giving off heat.
Oh, yeah, plenty of heat, and it's going to last for many tens of billions of years. It's going to take it a long time to cool.
So, is it possible? I don't know if there's any existence after it already went through the stage of expansion. If there's still any planetary bodies around it that could also be in a habitable zone in a white dwarf.
The only problem with that is that the white dwarf is illuminating and causing ionized glow of gases that it expelled up to 2 light years away from itself.
Oh, okay.
So that whole region is going to be a highly irradiated no-go zone that would deal us a very unfortunate blow.
Yes, no,
it would unalive us.
I had to ask, but that makes sense.
Yeah. Now, and the white dwarfs are not the end of it. Okay, there's more. But let me just finish this. If I could take a teaspoon of white dwarf material and take it out of the star and put it on the Earth, it would weigh as much as a car. It would weigh 2 tons. A little tiny teaspoon.
It's so dense.
It's so dense. Okay. And it'd be mostly carbon and oxygen atoms. Okay. How about that? Wow. So that weigh about 2 tons, maybe a little over. Now, the temperatures, okay, are interesting. Now, these white dwarfs are, in some cases, thousands of light years away. Okay. Like in the Helix Nebula or in the Ring Nebula. Yet, in our Sky Tour live stream telescopes, we can see the white dwarf glowing right in the center. Wow. Now, it's the size of the Earth, and it could be 600 light years away. It could be 1,000 light years away, 5,000 light years away, and we can still see it.
Is that the luminosity level?
No, because the white dwarf technically should have a low luminosity. If we look at our chart again, okay, we bring this up. That's the wrong chart. That's the other evil chart you don't want to see. If we bring this chart up, okay, look where the white dwarfs are, right here. Okay, they're down there, low luminosity.
Yep.
Now, that's because they're so small. They actually are, because they're so small, they don't have a lot of diameter. Again, they're the size of the Earth, but how come we can see them from so far away? It's because they are so hot. Their temperature are between 40,000 Kelvin and 72,000, which is 72,000 Fahrenheit, just so you know. Okay. Now, when they're first formed, okay, their temperature is about 180,000 Fahrenheit or 100,000 Kelvin. Okay. 180,000 Fahrenheit. That's how hot the surface of a white dwarf is when they first emerge from that planetary nebula or what they're seen there. Okay. And as they mature, the average temperature becomes about 72,000 Fahrenheit. Okay. Now, that's a lot cooler than the star's core before, but it's actually a lot hotter than the star's surface was before.
Right.
Okay.
Right.
So the surface, not the core. So you got to make that distinction. So, and the thing is, this isn't the be all end all for, things that want to take us out in the universe. But there's another one called the neutron stars. And the neutron stars are even more incredibly, I should say, bad, unaliving. Okay. So a white dwarf, though, it'll probably take more time to cool than the universe was in existence.
So
So
I just want to, because I'm learning, obviously. So
yeah.
you've got the novae, you've got these dwarfs, and then you've got the neutrons. Are those the main effects that these suns go through?
Yes. All stars will go through some form of end state. In stars that are like the sun or a little bit more massive, it'll be the white dwarf stage with the nebula that ends up, glowing around that white dwarf for billions of years. In the case of more massive stars, like say Betelgeuse or Antares, all right, we get something even more interesting here. Okay, now the neutron stars are the collapsed cores of very massive stars that have gone supernova. So when a star finally runs out of all of its fusion fuel, the outer layers just come rushing in because there's nothing pushing out anymore. So it just goes from all sides. That immense collapse does several things. First thing is it will start this massive explosion. And what happens is the stars are generally really large, right? They're going to be supergiants. So they could be out if you put, say, Betelgeuse, where the sun is, it'd go all the way out to Jupiter's orbit. And you got to make that a sphere. So you can see that if the star was undergoing a supernova and its core collapsed, then that stuff's going to start moving out from the center of the star. But it's not going to show up right away. It's going to take hours to breach the surface of the star, right? So because of that, we end up not seeing the supernova exactly when it happened. We see it hours after it started. Okay, so when we see it visually, we know it had already been underway for maybe hours. Okay, now what's interesting is I'm going to bring this table up now. Look at all the different colors. Okay, now the Big Bang made the elements in blue. Dying low mass stars like our sun, when it dies, are going to make these. Okay, that's a whole nother talk. But look at the yellow. Massive stars that explode make all those elements in the periodic table.
Wow.
Okay, and it's a mixture of all of them. Now the stars will make hydrogen, helium, carbon, nitrogen, oxygen, fluorine, neon, sodium, magnesium, aluminum, silicon, phosphorus, sulfur, chlorine, argon, etc. All those yellows, all the way to iron, number 26. Normally, okay, it'll do that normally, these big massive stars. But then the supernova makes these additional yellows after that, and the previous ones as well. So we're talking about stars as element factories, and they will actually create these many different elements in their existence. And they do that in the supernova in particular, because when we talk about the supernova, we have to talk about the end state. What's the end result? What happens after? Okay. Now, stars are hot. Okay. And their composition, as I said, is made up of plasma, which are just protons and electrons, all separate from each other. Okay. Because it's too hot in the envelope of a star, a normal star, okay, to actually maintain an atom of any consistency. Okay. So when this, during the collapse, the electrons that are floating free with these protons get slammed together into the nuclei. So here's how that works. Remember, it's plasma. Protons are running around, electrons are running around. Now the star is collapsing. The core within which these things is getting compressed, and the protons and the electrons are being pushed together. Okay, when they're pushed together really violently like that, what ends up happening is you can actually make a neutron. Okay, so when the electrons get slammed into the protons, you get an electron. Okay, I'm sorry, a neutron. So it's a P plus E, proton plus electron yields a neutron, plus something called an electron neutrino, a little energy thing that comes shooting off. Okay, now that compression, just imagine that going on all throughout the core. All right, this is a process called neutronization. It actually makes the neutrons. So when we talk about this getting collapsed, what's going on in that core now is that the core is being filled predominantly with neutrons. And so this compression makes this massive neutron star. And so we look at how compressed that is. If we compare the size of the neutron star to the Earth, the white dwarf was about the size of the Earth, right? The neutron star is the size of Manhattan Island.
Oh my God.
Yeah. And that can be represented like this. This is a neutron star visualization.
Can you see them when you're doing your observations with the telescope? Or I'm sure
We'll talk about that in a minute, because
we only got about 5 minutes. Just letting you know.
I know. So the neutron star basically is literally about 1.5 times the mass of the sun, in the size of Manhattan Island. Okay, about 12 miles in diameter, so they're very small. Okay, has a solid crust, about a mile thick, and then a heavy liquid interior, mostly of neutrons with some other particles. Okay, so that is the weirdness of the star. Right now,
that is wicked. It's liquid inside. It's got a hard shell on the outside. That's wicked.
Yeah, it's like a billiard ball on the outside. However, if you crack it or you merge them, you get this massive explosion that sends out gravitational waves that we've seen. So really immense stuff. So now we have this neutron star. Now, the initial temperature of these things at the moment that they're made is literally 180 billion Fahrenheit. I mean, almost an impossible temperature to believe. That's 100 billion Kelvin. The surface temperature after a few years, as it cools down, is only about 1 million Kelvin. Okay, and then as they get older, over millions of years, they continue to cool between 100,000 Kelvin and 500,000 Kelvin, which is about 900,000 Fahrenheit. So nice and chill, right? Nice and chill.
Oh
okay. Gosh. Now to answer your question about seeing them, they're only 20 miles across.
Right.
And they are very bright, but they're also low in that luminosity, that thing I talked about. Okay. They're way lower luminosity than those white dwarfs down there. Mm-hmm. Okay. Now they're hot, yes. But neutron stars are so small that they're really hard to visualize. Okay. Now the other thing is they're distant, they're small, okay, and they give off most of their energy in X-rays, way far beyond the blue visible part of the spectrum, way into the high frequency part of the spectrum. We can't see it with our eyes, but most of their energy is given off in X-rays. Okay, so with that, we have to say, holy cow, these things just don't. They actually know no quarter. There's no way to survive an encounter with a neutron star in any way, and because they are more massive stars, they actually have a much bigger area of influence because they were more massive stars. The neutron stars, incredible. Now, just to close it up, whereas a teaspoon of white dwarf material would weigh about 2,000 pounds here on Earth, a teaspoon of neutron star material, are you ready? Mm-hmm.
Oh.
Over 1 billion tons.
Wow, that's how.
Teaspoon.
Oh my God. And it's liquid inside, and it's still that density.
Yeah. So and sometimes you take one of those stars that is this big, as I said, like this big here. Okay, these stars rotate because they're the remnant cores of these massive stars, and they rotate so fast. They stay together in spite of that because of that massive gravity that they have. So in the Crab Nebula, for instance, that we often image in the Crab Nebula in Taurus, a supernova remnant, we see that's one where we can actually see the Crab pulsar because it's flashing at us in a hot spot, so we can actually see it visually. Okay, it's spinning 33 times per second. A 22-mile diameter object spinning 33 times per second.
That's insane. Just thinking of that is crazy.
And it's slow. Oh, it's slow compared to the winner. You know how fast the fastest pulsar spins? 716 times a second. That's just like.
Before we wrap up, have we ever witnessed a collision with a neutron star?
Yeah. We've seen gravitational waves that were emitted by collisions of neutron stars. And by the way, going back to this diagram, I want you to notice we have merging neutron stars in purple. See that?
Wow, yes.
Okay.
Merging neutron stars?
Yep, that is where neutron stars collide with each other. And notice number 47 in the periodic table. That's gold. Most of the gold created in the universe was created by merging neutron
That
stars.
is amazing factoid right there.
So all the gold we have on Earth once started its life from a neutron star collision. So there's been a lot of that stuff happening.
There's a lot of purple or what, lilac, whatever color that is. Is that all result from the neutron?
Yes, that's everything in purple here. Notice it says merging neutron stars. That's where all these elements come from.
Wow, that's a lot on the table.
Yeah, it is. It's a tremendous amount on the table. It's incredible. So, the next time you see this chart, it doesn't really tell you much.
No.
But understand that all of these elements were created in the heart of the star under various conditions.
Wow, that's amazing.
Supernovae in yellow, merging neutron stars in purple. Okay, crazy stuff. We haven't even talked about cosmic ray fission. Never mind that. Okay, that was the red. But anyway, so you see, guys, this is part of why the universe is trying to kill us. It's trying to hurt us. All these things. But next week we'll probably talk about the deadly planets.
Well, the following week, the next week's the holiday.
Oh, next week's Easter, yeah. So we won't talk about them, but the following week we'll actually talk about killer planets out there that want to really do us in. Oh my
gosh. Well, you know what, Tara, good luck.
That's right. She's going to be here.
She'll be the one to have dreams after that conversation because, like somebody said in chat, I'm going to go. I learned a lot tonight.
It's a really interesting topic,
That is fascinating. I did not know that. A lot of that at all. That's why it's always awesome to be here with you.
Yeah, it's great, man. I appreciate it. Thank you for taking on the charge to actually come here and be tortured.
It was great. It was fun
and frightened out of your mind.
You had to deal with me more than I had to deal with you.
Yeah, it's fine. That's fine. I always joke around with him, but the truth is, he's all right. He's done a great deal of good things for us.
Anyway, Mark,
and for you guys. So, guys, thank you for coming. It was good to see you here on Unexplained Network. And I'm here with our great producer, Bill, courtesy of Race Hobbs and Margie K. This is our second show on the network, and we're going to continue. I did like 80 or 90 on the other network. And so we're going to have to build up that number here, too, won't we?
New frontiers, baby. New frontiers.
Yeah, that's right. Well, guys, thank you so much. And as always, keep looking up and make sure that you join us here not next week, but the week after. All right. So you have a good night. Good night, everybody.
Good night, everybody.